So hello everybody. So we are going to start. So this is lecture 3. Okay. All right. So today we are okay. So let's move on. So let's talk about the logistic equation. So this means different things, but so we are talking about the continuous ODE. All right, so we're dealing with growth populations. All right, so in 1798, Malthus proposed a model to describe the evolution of population, the number of people in some country or something like that. So it was first published anonymously, but it was later found out that Malthus wrote this paper. So Essay on the Principle of Population. And so the model is like that. So the evolution of the number of people in some place equals the birth of rate minus the birth of death, and it depends on the number of people. The more people, the more birth relatively with this rate. Okay, so can you compute the solution of that? So B and D are constants. So what's the solution of this equation? So we have seen that a couple of times. So the solution is an exponential, right? And so if x0 is my initial number of people at time 0, then the solution is given by this expression. So if in this model, if the rate birth is greater than the death rate, so if the birth rate is greater than the death rate, then you have an exponential growth. And if D is greater than B, then you're going to 0 exponentially fast. So it's not so realistic, but it worked in this period. It worked actually. Okay. Yeah, so this is an exponential growth and this is an exponential decay. Okay, so after that, well, yes, so you can have a look at this book. You can find it easily. It's the book of Murray, Mathematical Biology, and you can find a lot of information there and a lot of mathematical models for biology. Okay, in particular, these few equations that we are going to see are inspired by this book. Okay, so then Verhulst. Okay, so Verhulst was not satisfied with the Malthusian model, and so he tried to change the equation so that you will not have exponential growth indefinitely. All right, so in 1838 and 1845, there is 2 papers, and this is the model, right? So if you take A to be B minus D, you can see that. So this is new, right? So x prime equals ax. This is the Malthusian model, and Verhulst added this term. All right. So the new rate depends also on x divided by k. So the k is important, and it's called the carrying capacity. So this term, you will see, implies that you cannot grow exponentially indefinitely. All right, so we are going to see that with the math. Okay, so I propose you right now an exercise, and I let you with that. So x is takes value in R, so it's a one-dimensional ODE, right? So we look for a solution x of t, and we assume that at time 0, x belongs to 0 and k. All right. All right. So yes, we make this assumption, which written here, x0 belongs to 0k. But for the beginning, you don't need that. But after, yes. So I let you solve this problem, and I let you a couple of minutes. Let's say 15 minutes. Okay. So you have 15 minutes to try to solve this exercise and to think about it. Any questions so far? If you want to ask a question, you can unmute yourself and ask your question. All right. All right. So see you in a couple of minutes. All right. So next we are talking about the Lotka-Volterra equations. So those equations appeared in a few papers from Lotka between 1910 and 1925. So for example, here on the right here, those are the Lotka-Volterra equations, right? So it's in a paper of Lotka in 1920 for chemical reactions. All right. And so it's hard to find the original paper of Volterra from 1926, but there is a note on Nature which describes the phenomena and the equations and all that. Everything is written here. For example, the proportional rate of increase of the eaten species diminishes as the number of individual of the eating species increases. So we are going to talk about that in the next slide. All right. Okay, so those are part of the original works of Lotka and Volterra. Okay. Okay, so let's move. And so those are the equations, right, that we are going to consider. Yeah, so let's just comment on that. So here, U represents so Lotka-Volterra equations are prey-predator systems. Okay, so the U is a prey. For example, a rabbit or some fish. And so you see, forget. Let us assume that we don't have predator. So V is a predator. So if you assume that we don't have predator, you just have U prime equals AU. So everything is positive here. A, B, C, D are positive numbers. So if you forget about the predator, you just have the Malthusian model, and you have an exponential growth, right, of the prey. But you have a predator. So V eats you. So V eats you. So the rate, the effect of the predation on the prey is that there is these terms, right? You can find it here in some written here, all right? Okay, so there is a minus BV times U, and the minus BV, in fact, enters in the rate. So when the predator eats the prey, there is this term. And in absence of prey, the predator dies, okay? Its population goes to 0 exponentially fast, and the rate is D. But since the predator eats the prey, the population of predators increase with a rate which is proportional to the product U times V, all right? So those are the Lotka-Volterra equations, right? So it's an interesting example in ODE applied to biological problems and population estimations. All right. Okay, so next we are going to solve an exercise. All right, so you got that. Okay, so I let you try to solve this exercise. So it starts as usual, and you can just think. So at the beginning, you've already done things like that, and after you have to think more about it. But I let you like 15 minutes again. Actually, yeah. So we can make a break. All right, you can make a break. So we are going to make a break plus 15 minutes of you try to work. So just make a break and start to work. And so within the two, we come back in half an hour. All right. And then we are going to be together until 7 p.m. France, 1 p.m. United States. All right. So see you in a few. All right, so we are now going to correct. I have seen a few answers, so let's go. So we are considering this equation. No, not good. Sorry. Okay. So we are looking at wow, it's crazy. Sorry, so I'm not going that. So I'm going to make it on the board because it's better. So sorry about that. Okay, so okay, so here are some trajectories corresponding to different initial conditions. So here are the solutions. So if I start with an initial condition here, so if I start with an initial condition here, I will go like this, and I come back. So here, if I start with an initial condition here, when time moves, the solution goes like that. But if I pick up another solution, then the solution goes like that. All right. And the same here for the purple. All right. And so at the right is for one of these solutions, I can see that's the purple one. You got u as a function of t in purple, and in green it's v. And in green it's v.
Monsieur,
Oui.
on a dit que HUV, c'est un constant.
Yes.
Mais V dépend de T, non? Donc, même U aussi.
Oui. Yes. So v and u, no, v and u are not constant. V and u are not constant, but I can write something. But here you have that h of uv of t so h of u of t equals, it's a constant. When you move here, this curve, this closed curve, corresponds to HUV equals a constant. And here, it will be another constant. And here, another one. So each constant gives you a closed curve, and this corresponds to a trajectory, or a class of trajectory, but yeah. Did you get it?
Mais HUV qui égale à A ln du V moins BV plus D ln du U moins CU. Donc
Mhm.
là, c'est en fonction de U et V.
Yes, yes, but U and V change, but H doesn't change. You know, you can plot it. You can plot it. It's PD. You can come on Friday and we can plot it together. You will see that, for example, the purple curve, you have different U and V, right? Here you have some U and some V. Here you have another U and another V, right? But H is the same value. So for this point and this point, H has the same value. And the trajectories, this trajectory remains on the H for which HUV corresponds to this C. You got it? H here is a constant. That's the point. The U and V moves with time, but they move within constant value for H. Think about that, okay? Think about that, and you can come on Friday on the office hours, all right?
D'accord, merci beaucoup.
You're welcome. All right, so another question? So if not, yeah, so now I will discuss some numerical methods. For example, when you see these pictures have been drawn with the computer, okay? So they are approximations of the real solution. So to compute a solution that will be close to the solution, what we are going to do. So let's assume now I'm talking about numerics. So I want to draw. Sometimes you cannot compute the exact solution of my solution. That's the case for Lotka Volterra. We have computed we have an integral solution. That's what we call that. My function h, but usually you cannot compute u of t and v of t. All right. So we are computing, approximating the solution of u prime equals f of u on a finite time, on a finite interval of time 0 t. All right. So t is my final time, and 0 it's my initial time. All right. And so I divide here my interval into n subintervals. Okay. And now I will approximate my solution on the time interval 0 t by a vector of numbers or vectors. So in general, each ui is a vector, all right? But I have a finite number of vectors, all right? And h is the t, the final time divided by the number of intervals here. And so here it's h. The distance here, it's h. So it's t divided by n, all right? So the simplest method is, you see, you can approximate the derivative by ut plus h minus ut divided by h, and you get that. All right. So this is the Euler method. I'm sorry. This is the Euler method. But usually, so I give you the most used method. It's the Wunsch-Kutta 4 method. So the idea is close to the Euler method, but instead of just taking f of ui, I will compute 4 numbers. I don't give the details. We could spend a lot of time on that to understand very well the method. I just give you the method so that you can implement it on your computer. So I will compute these numbers, and it's an improvement of the Euler method. All right, and you compute these numbers. So each number is kind of the number you compute when you do the Euler method, and then you average these 4 numbers. There's a mistake here. I forgot 2. You know, it's a mean value. So here there's the 2, and here there's the 2. All right. Okay, so this is an algorithm to approximate your solution, right? So h needs to be small if I want to get a good approximation of my solution. All right? Any questions? So,
Monsieur,
oui, yes.
comment on obtient les UI?
So you got U0, right? You got U0, all right? F is known. So U0, it's your initial condition. It's the same. So when you got U0, you just apply that, and you got U1 here. All right? You start with I equals 0, which is known. You choose it usually, and you get U1. And then you get, once you have U1, you can compute U2. So you do it by step. So it's an explicit method. All right. Once you have U0, you can compute U1. Just apply that. And once you get U1, you can compute U2, etc. You got it?
Yeah, thank you.
All right. Another question? All right, so if there's no question, let me do something. So I will show you an example, all right? So, but let's move on. Okay, this is the Lorentz equation. So Lorentz worked on the forecast, la météo, okay? And so he was working on the simplification of the Navier-Stokes equation from fluid mechanics. And he used this system, right? Okay, so I'm just going to show you on the laptop some computations with the Wunsch-Kutta 4 method of this system. All right, so let's do that. Just need. Okay. Okay. looks like okay. So here you can see it's a program in C++ which simulates the Lorentz equation. All right. Okay, and the Runge-Kutta method appears here. Right, this is my K1, but since I have 3 variables, there is 3 values for K1. So my K1 is here, it's a vector of 3 numbers. The same for K2, the same for K3, the same for K4, and then you can see here my dt corresponds to the h, and here is the formula. All right. Okay, now I'm going to run the simulations and to show you the solutions. So first, I have here pre-selected a couple of variables. So let's start with so sigma is 10, my rho is 0, and my beta it's 8 divided by 3. So sigma and beta will not change, but I will change my rho. And so I save it and I compile it. I just run. Okay, it's finished. Now I'm going to show you the solutions. So there's 3 variables. I can have a look at them. So it looks like the solution, my initial condition starts here, and I'm converging towards 0, 0, 0, which is a stationary point. All right. Now, so I can show you also, for example, the x as a function of t. Okay, you can see that it decreases towards 0. All right. This is just to give you some insights about the numerics for computing solutions of ODE. Okay, now I'm going to change the parameter 0, the parameter rho. Okay, I'm going to take it equals to 6. All right. Again, so sorry. Right. Oh, again, it converges for the specific initial conditions. It looks like it goes to a stationary solution, but it's not the same. So let's look at the 3D representation. Okay, so typically this is, it looks like, so it's in 3D, but typically this trajectory corresponds to a focus. So it looks like one of the eigenvalues will be negative and the other one will be complex with negative real parts. Okay, this is typical from a focus, right? So it looks like for the first value, the stationary point was a node, a stable node, and here it looks like it's a focus, right? So we should define the focus in 3D, but typically the projection looks like a focus, all right? So definitely I will have here two complex eigenvalues with negative real part, and the third one, which will be real, also is negative. All right. So I continue. I move now. Let's look at 12. Let's look what is going on at for rho equals 12. Okay, it looks like it goes also to a stationary solution, but it's quite fun. It goes, it looks like it goes somewhere and then it comes back and goes to a stationary solution. Right, let's continue. Let's continue, and I'm taking the next 20, field 20. Yeah, we can. So we can look at the, let's. Yeah, there's a lot of oscillations, and then, okay. So here it was 20. No, let's look 22. 22, sorry, 22. All right. 22. Okay. Oh, who knows this picture? Let's look at the x as a function of t. Yes, that's chaos. Yes, so that's the typical example for the chaos and the picture that you saw before. So chaos, because so there are several definitions of chaos. I'm not going into that, but you know, it's unpredictable. You know, you cannot predict what's going on. It's very hard. So on this picture is, yes, it's the Lorentz attractor. Well, it's very well known. So yeah, this is the basis of chaos theory. Okay. All right, that's what I wanted to show you. Now let's get back to there. Okay, so this was SIR. Yes, Lorentz one is chaotic depending on some values. That's right. So now this was the theorem for SIR, but yeah, I'm not going to talk about that. Okay, now let's get to projects. So for the students of Le Havre, it's mandatory. You can work if some people want to work with you. It's fine. Usually they got already some master degree, so it might be good for Le Havre students. But so for you, it's mandatory because you will get a grade. And so here are some projects. Okay. You have 2 weeks. You have 2 weeks to choose one of the projects. So I just put you the titles here. You can do some research, or you can talk with me to get more information about them. And you have 2 weeks to make a choice. All right. And so, yeah, so there is 9 projects. So you can make a team to work on that. Of course, I don't want. Yeah, you can choose one, but it's better if you team up with somebody of the Havre. Yeah, you can choose one, sure. Okay, and then so here are the projects. First project, it's about Hodgkin-Huxley. The first thing is you have to understand, to try to know how did they obtain their equations. It's a modeling question. Okay, you have to go into the details. Then you can do some math and numerical simulation. So the first one is Hodgkin-Huxley with a part of modeling. All right. Project 2. So there is a theorem. There's a theorem. This is math. This is pure math. You don't need to do any numerical simulation, but you have to go into the proof. All right. So there's a proof. It's not usual to find it. I can give you some notes on this proof. It's from the Hudson School. It has 40 years, the proof. And you know, sometimes you have limit cycles. And the proof is about the stability of a limit cycle. All right. So it goes beyond our course, but it's a project. So it's a mathematical proof. Again, you have some proof in the book of Perko. I will provide you the references. And you have a proof of existence of a stable invariant manifold. You can see that when you have stationary solutions and your solution converges to a fixed point, you have some stable invariant manifold in there. So it's also a proof. The fourth, it's the Fitzhugh-Rinzel model. All right. So it's like a Fitzhugh-Nagumo, but you add a third variable, which is super slow. So first, there is 2 projects on Fitzhugh-Rinzel. The first is general, so you have to do some numerics on math, and it's usual. You do some stability analysis and so on. And the second aspect is to take advantage of the slow-fast parts. Okay, so there are 2 projects on that. 6, it's about SIR models. So in the slides, you saw some slides about SIR, but I didn't talk about it. So there's a project on that. You have to prove a theorem, do numerical simulations, and try to grab some data, some real data, and work on it. Okay. 7, it's Lorentz model, numerical and theoretical. 8, the 3-body problem. For example, the idea you took the sun, you choose the sun, you choose the Earth, you choose the March, the planet March, and you apply the Newton gravitational laws, and you get an ODE. So again, you do some research on this thing and you numerical simulations, and you do whatever you can. And 9, it's about Lotka Volterra model, but we did all the stuff, but we can choose some kind of model which is close to Lotka Volterra, little bit different, and you work on that. All right. So that are the projects. Okay, so that's it. If you have any questions, I will happy to answer. Okay.